There are many versions of Cauchy Schwarz inequalities depending on what vector spaces and inner products we are talking about. In this video, I will discuss the most elementary versions. I will focus on their relations with another type of inequalities, also very important, called Arithmetic-Mean-Geometry-Mean inequalities. Let A1, A2 to AN and B1, B2 to Bn be real numbers. Then A1 times B1 plus A2 times B2 to plus AN times Bn is less than or equal to root of A1 squared plus A2 squared plus up to AN squared times root of B1 squared plus B2 squared plus up to Bn squared. A trivial situation is the right-hand side equals 0. Then either a1 squared plus a2 squared plus up to an squared equals 0, or b1 squared plus b2 squared plus up to bn squared equals 0, which means either a1, a2 up to an all equals 0, or b1, b2 up to bn all equals 0. Either case, the left-hand side is 0. So from now on, we simply assume the right-hand side is not 0. Then must be positive. So the objective is to prove the left-hand side divided by right-hand side is less than or equal to 1. The first term of the left-hand side, a1b1, divided by right-hand side, is less than or equal to root of a1 squared times root of b1 squared divided by right-hand side. This is because root of a1 squared times b1 squared is simply the absolute value of a1 times b1. Now, the expression is in two colors, the red portion and the blue portion. So it is square root of the red expression times square root of the blue expression. This is simply the geometrical mean of the red expression and the blue expression. So by AM-GM inequality, it is less than or equal to the arithmetic mean of the two expressions. The equality holds when a1b1 equals the absolute value of a1b1 and the red expression equals the blue expression. We can simplify the two conditions. Taking square root of the second condition, it would be a1 to b1 equals positive or negative of the ratio of these two expressions. However, we know from the first condition that a1 to b1 cannot be negative. This is what we just proved. We can simply establish estimate for the other terms on the left-hand side divided by the right-hand side. a2, b2 divided by right-hand side up to an, bn divided by right-hand side. Sum up all the inequalities. We can see all the red expressions sum up to 1 and all the blue expressions sum up to 1 as well. And the inequality is proved. The equality holds when a1, a2 to an and b1, b2 to bn are proportional and they are all positive. Let's look at the inequality again. It works for all real numbers. Of course, we can replace b1, b2 to bn with the negative of these numbers. Then the inequality becomes negative of a1, b1 plus a2, b2 plus up to an, bn is less than or equal to the product of two square roots. Combining this with the original Cauchy Schwarz inequalities, we have a stronger estimate, and the equality holds under a weaker condition, and the A1, A2 to AN is proportional to B1, B2 to Bn. A short discussion on the geometric background. A1, A2 to An and B1, B2 to Bn are two vectors in the Euclidean space Rn. They are labeled as A and B respectively. We can define Euclidean norms or two norms of the vectors. For example, the two norm of vector A is defined to be the root of the sum of the components squared. The left-hand side of the inequality A1, B1 plus A2, B2 plus up to AN, Bn is called the inner product of the two vectors. Also, if the vector is scaled by divide by its two norm, we come up with another vector denoted by the A0 and the B0. These are called normalizations of the vectors because the normalized vectors have two norms, 1. In terms of vectors, Cauchy Schwarz inequality is stated. The absolute value of inner product of two vectors is less than or equal to the product of their two norms, and the equality holds if and only if the vectors are linearly dependent. We can generalize the inequality into three vectors. For simplicity, we assume all the components are positive real numbers. The left-hand side is A1, B1, C1 plus A2, B2, C2 plus up to AN, BN, CN. This is a generalization of the inner product of two vectors, and the right-hand side is simply the product of three norms of the vectors. The proof is similar. First, we define A to be A1 cubed plus A2 cubed plus up to AN cubed, and B and C are defined in a similar way. Then, each individual term on the left-hand side, AI, BI, CI, divided by the whole right-hand side, it can be expressed in the cubic root of AI cubed times BI cubed times CI cubed divided by A, B, C. This is just the geometric mean of three numbers. By arithmetic-mean geometric mean inequality, it is less than or equal to their arithmetic mean. And we sum up all the inequality for I equals 1, 2, up to n, we will prove the Cauchy Schwarz inequalities for three vectors. From these two proofs, we can see how Cauchy Schwarz is related to AM-GM. A Cauchy Schwarz inequality is essentially a system of uniform or homogeneous AM-GM inequalities. We will see this relationship by an example. Let A, B, and C be positive numbers. Prove that A squared B plus B squared C plus C squared A is less than or equal to A cubed plus B cubed plus C cubed. First, we can prove this by AM-GM inequality. The first term of the left-hand side, A squared B, is actually A times B, which is the geometric mean of A cubed, and B cubed. Of course, they are less than or equal to the arithmetic mean of the three numbers. And similarly, we have estimates for b squared c and c squared a. Sum up, we prove the inequality. But clearly we can see we are using 3 AM-GM inequality uniformly. So they might be able to combine into a single Cauchy Schwarz inequality. Let's see this. Of course, this is not a new proof, this is just a different presentation. The left-hand side of the inequality is actually the sum of a component product of 3 vectors. Red vector A, B, C, green vector also A, B, C, and a blue vector B, C, A. Then, by Cauchy Schwarz inequality for 3 vectors, it is less than or equal to the product of the 3 norms of the vectors. And the proof is done. Thank you for watching.